All right, welcome to section 1.6 from the OpenStax PreCalculus book. In this summary, I'll be talking about the absolute value functions. So absolute value functions, that's something that's already been introduced in your book. It was introduced in 1.1 as one of the toolkit functions. And you probably have some background in terms of what the absolute value symbols mean mathematically. For example, you probably know that the absolute value of -5, for example, is just equal to 5. Whereas the absolute value of +5 is just equal to 5. You're like, oh, right, that thing that kind of gets rid of negative signs. Yeah, that's true. But you got to be a little bit careful. The absolute value is a little bit more tricky and subtle than some people give it credit for. So let's see. Can we say that the absolute value of -x equals x? Question mark, right? If you're kind of following through this example, you're like, right, it gets rid of the negative. If that's what you're using for your definition of absolute value, you might think that the absolute value of -x equals x. But in fact, that's not true. Wait, what? That's not true? Well, it's not always true. There are values I can plug in for x into this equation that will make this not true. It will make it a false statement. Maybe I'll let you think no, I won't let you think about it for a minute because I can't stand just dead air. For example, I don't know, maybe x equals -3, right? Take this equation, which I shouldn't even call it an equation because it's something that's false, and everywhere you see an x, change it into a -3. So the absolute value of the negative of, and then instead of x, I'm going to write -3. And my question is, does that equal, I'll replace this x with a -3. And I'll put the question mark here because this is not a true statement and I don't feel very good writing false things down with an equal sign inside of it. And to show you why this is false, well, the negative of -3 is just 3. And so does the absolute value of -3, the absolute value of 3 equal -3? No, that's not true. The absolute value of 3 equals +3, not -3. So the point that I'm making is you got to be a little bit careful with absolute value. Maybe it's a little bit more subtle than you give it credit for. So that kind of brings us to the first of our main topics. Okay, so then how can you define an absolute value? Like I sort of have this idea of what it means, which is good, but how can you come up with a concrete definition? Well, here's one way. The absolute value of x, I could define it piecewise. So I could say it's just equal to x if x is greater than or equal to 0. However, if x is less than or equal to 0, less than 0, not less than or equal to, it's equal to -x. Truth be told, you could put the underline here or here. It makes no difference. But this is the common definition that you see. And you're like, whoa, I thought I understood absolute value, and then I started watching your video, and now all of a sudden I'm confused. Like, that's kind of a complicated statement. Well, it's not as bad as it seems. It's just kind of saying that if the number x right here is something that's greater than or equal to 0, like 5, for example, then the absolute value signs don't do anything at all. The absolute value of 5 just equals 5. However, you have to be a little bit careful if the thing inside the absolute value symbol, the x, is less than 0. Like up here, the thing inside the absolute value symbol is less than 0. Then you need to change its sign. This does not mean it'll be negative. It means you're changing the sign of the thing inside the absolute value symbols. So if the thing inside here, if x were equal to -5, this would be saying, oh, then it turns into the negative of -5, aka +5. So maybe that makes sense. There's other ways you can define the absolute value. Maybe I'll write or here. You could say that it's equal to, I don't know, the square root of x squared, for example. I'll let you try that out, but try throwing in any value for x. Try throwing in -5 or 3 or 2 or 0 or -1. You'll get a true statement here. This is another way you can define the absolute value of x. Your book uses this top one up here. To be perfectly honest, I think more important than either of these mathematical definitions is just sort of having an intuitive sense of what it means. So I'm going to say intuitively, I think that's spelled right. The absolute value of x is the distance x is from 0. So what I mean is if you draw a number line, here's 0. The distance between -5 and 0 is 5. Right? If you're standing right here and you got to walk here, or if you're standing here and you got to walk here, either way you got to walk 5 units to get there. And similarly, the distance from 5 to 0 is 5. And that's why the absolute value of both -5 and +5 is equal to 5. So, okay, if you can understand how these things correspond with this idea, that's great. But realistically, we won't be using these definitions a whole lot, although it doesn't hurt to know them. But having this intuitive understanding of what this thing does and how it depends on whether what's inside the symbols is negative or positive will really be the key idea for this section. And so what I'm going to try to do is give you some concrete examples. We're going to solve some equalities or some equations, some inequalities that have absolute values in them. But before I do that, I want to kind of piggyback off something from the previous section, the graph of the absolute value. You're like, wait, graph of absolute value, that wasn't the previous section, that was section 1.1. I learned in my toolkit functions that the graph of the absolute value of x, if I want to create a function and say f of x equals the absolute value of x, his graph looks like this. It's kind of the V-shaped graph. And that makes sense if you put any positive number into it, like 3, for example, what comes out is just 3. Over here on the positive side, the graph looks like f of x equals x, another one of our toolkit functions. But over here, it's not quite x. If you're familiar with linear functions, it's actually negative x. The slope is -1 here, which is exactly what my piecewise function says that it should be. At any rate, you're like, wait, why is this a topic now? I thought we were past all this. Well, let me try giving you another example. What if I said g of x was equal to, and let's see, how crazy do I want to get with this? 2 times the absolute value of 3 minus x minus 1. Wow, what a mess. You can come up with this graph right here. You're like, yeah, of course I can. I got a calculator. Without a calculator, you can come up with this graph right here. Using the methods of section 1.5, you can come up with the graph of this function right here. Because this is just a whole bunch of transformations. I think there's going to end up being 4 transformations going on here of this function. To see the transformations, it helps to write this thing slightly differently. Instead of 3 minus x, I'm going to say it's negative x plus 3. And then it'll look more like a form that I'm familiar with when I'm dealing with all the different transformations. I have 2 vertical transformations, this 2 right here and this -1 right here. So if I apply the vertical transformations, remember that the order you apply them in is you do the multiplication first and then the addition second. So I'm going to take all the old y values, I'm going to multiply them by 2, and then I'm going to add -1 to all of the old y values. So this y value was 0. 0 times 2 is still 0. Minus 1, it's going to move down here. This y value was 1. 1 times 2 is 2. But 2 minus 1 is just 1. So this will move right here. This y value is 2. 2 times 2 is 4. 4 minus 1 is 3. It'll go here. And if you plot a couple more points, what you'll end up seeing is that if I just apply the vertical transformations, I end up with this graph right here. This is not my answer because I've just applied the 2 vertical transformations. What I want to do now is apply the horizontal transformations. So to apply the horizontal transformations, again, note that you have 2. You have this plus 3 right here. So I'm going to subtract positive 3 from all of my x coordinates. These are horizontal transformations because they're affecting the x, not the f of x. And then I have this negative right here, which tells me I'm going to divide all of the x coordinates by -1. So dividing all the x coordinates by -1 and subtracting 3 from all of the x coordinates. However, remember that the order for horizontal transformations is goofy. Everything's backwards. So I'm going to first subtract 3 from the x coordinates, then divide them by -1. So this x coordinate is 0. If I subtract 3 from it, it goes over here to -3. But then if I divide that by -1, it jumps over here to +3. This x coordinate is -1. If I subtract 3 from -1, I'm over here at -4. But if I divide -4 by -1, it jumps over here. And if you plot a bunch of other points, what you'll end up seeing is that you end up with, as your final graph, it's hard to draw on a computer, as you've heard me complain before, you end up with this guy right here. This guy in red would be g of x. And so the first point that I want to make is you can graph the absolute value function without learning anything from this section. Really just knowing 1.1 and applying the methods, the transformations of 1.5. You can come up with the graph like this one here in red, g of x. I'm going to copy that over here because I'm going to use that same graph in different problems in this section. So bear with me for a minute as I try my best to copy this graph. And again, it's not going to look great. These are supposed to be straight lines. I could get some software that would draw straight lines for me, but I kind of like the freehand style. So I'm going to leave this and say this is g of x, which is equal to 2 times the absolute value of 3 minus x minus 1, because this was equal to this. So here's my function g of x. I would say that we've checked off the top 2 things here. We have a definition of absolute value, either an algebraic definition, piecewise or otherwise. And then also, maybe more important, this intuitive definition here. And then I've also talked a tiny bit about the graph of absolute value functions. And I say functions because there's really not just one. You can think of the thing in green here as the absolute value function, and then blue and then red being my final answer would be transformations of the absolute value function. The next 2 things I want to talk about really go hand in hand, and they illustrate how kind of subtle and tricky absolute value stuff can be. Solving absolute value equations. Let's say, for example, I gave you, let's see, should I write this in function notation? Sure, why not? I have this function g of x down here, and I ask you the question, find all values of x so that g of x is equal to 3. You could answer this question in a lot of different ways if you think all the way back to section 1.1. First of all, you could answer this just by looking at the graph. You could say, this is asking me the question, g of x equals 3, solve for x. Find all values of x that satisfy this thing right here. This is asking me the question, what can I put into the machine g, which is defined down here, to make 3 come out? So algebraically, I could say 2 times the absolute value of 3 minus x minus 1 equals 3. I could set this up as an equation. I could say the output for my function g of x is this thing right here. And so let's set that equal to 3 and solve this to see what I would have to put in. This would be one way you could do it. You could also get it directly off the graph. If you remember that the output for the graph is shown on the y-axis. So then you're just looking at this graph right here and you're asking yourself the question, when is the height equal to 3? Well, it looks like it's equal to 3 right here, and it's also equal to 3 right here. It appears that when I put 1 into this function or 5 into this function, 3 comes out. Let's verify that result algebraically, because what you'll see is some kind of tricky stuff happens algebraically. When I am solving, and this right here is what's called an absolute value equation because there's an equal sign, absolute value, because you got the absolute value symbols. When I'm solving absolute value equations, what I like to do is get rid of the absolute value. If there was no absolute value here, right? If these were parentheses, for example, instead of absolute value, this would be fairly easy. I think you could probably solve that, right? Isolate the x. But what makes it tricky is this absolute value signs. But I can get rid of the absolute value signs, but it's a lot easier to get rid of them if I have it isolated. So what I do when I'm solving absolute value equalities is I first isolate the absolute value. What I mean by that is maybe add 1 to both sides of the equation, and then divide both sides of the equation by 2. And that gets me here. The absolute value of 3 minus x equals 2. And at this stage, I want to get rid of the absolute value symbols, but I have to be really careful in how I get rid of them. In fact, in order to get rid of the absolute value symbols, I'm going to have to split this one equation into 2 separate equations. So I'm going to solve when does the absolute, so I have the absolute value of 3 minus x equals 2. And if you think about how that could be true, this thing inside the absolute value symbol, this 3 minus x, if this thing in here, which I don't know what it's equal to because I don't know what x is, but this entire thing, this entire 3 minus x, if that happens to be equal to 2, then I'll have a true statement right here, right? Because if this thing in here is 2, the absolute value of 2 is just equal to 2. Kind of like I wrote up here, the absolute value of 5 equals 5. The absolute value of 2 equals 2. So one way this statement could be true is if the stuff inside the absolute value symbol itself is equal to 2. But that's not the only way this statement could be true. If the stuff inside the absolute value symbol is equal to negative 2. Again, I don't know what the stuff inside the absolute value symbol is equal to because I don't know what x is, but pretend for a minute that you do know what x is and you figured out that this entire thing, 3 minus x equals negative 2. Then what you have right here is a true statement because the absolute value of negative 2 equals 2. So if this stuff inside the absolute value symbol equals -2 or +2, you have a solution. Most people just memorize that you go from here down to this step. But for me, it really helps to understand why you can go down to here, why you can drop the absolute value symbols, but for some reason you make two different equations and one of them's negative and one of them's positive. And the reason why is you think about what's inside here and what the absolute value symbol would do to it. Maybe you think about it in terms of this definition if you're really getting up to expert level stuff. So now I got two equations, and the nice thing about each of these equations is there's no absolute value symbols in them. So presumably you can solve them if there's no absolute value symbols. You want to isolate the x. Let's see, what most people do, which I don't really, this is how I do not do it, but I'll show you. Subtract 3 from both sides of the equation. If you subtract 3 from 2, you get -x equals -1. This 3 is gone, and this turns into -1. Then you're like, wait a minute, I don't want -x, I want x. So multiply both sides by -1, and that'll make this positive, and that'll make this positive. That's totally fine. Just FYI, that's typically not how I solve it. I don't limit myself to having my variable on the left-hand side. There's no problem with moving the variable over to the other side. I could make this 3 equals -2 plus x if I wanted to. And the reason I might want to is now my x is positive instead of negative. So when I add 2 to both sides of the equation, I have my x all isolated. I don't have to worry about this last step where I multiply both sides by -1. I don't know. Maybe you disagree. Maybe you'd rather leave your x on the left and you're like, it's not that hard to multiply both sides by -1. Fine, whatever. The point here is that I end up with two solutions. X equals 1 and x equals 5. Little commentary here. Something that you have to be really careful with absolute value inequalities is, imagine you had 3 minus x equals -2 here. So a different problem. If this were 3 minus x equals -2, you could still blindly go through and solve it. You could say 3 minus x equals -2 or 3 minus x equals the negative of -2. If you didn't really understand what you were doing when you split this equation into two, and you instead just memorized that you drop the absolute value symbols and put kind of a plus or minus on the other side, then what would happen is you would come up with solutions that aren't really solutions. Because if this is a negative right here, I should not get any answers, because there's nothing I could take the absolute value of to make the answer equal to -2. But if you don't really think about this and just kind of blindly solve algebraically, you'll still get solutions. So there's two things you can do. You can either be really careful when you're going through and doing your algebra and recognizing when there won't be any solutions, or you can just check your answers. And what I mean by check your answers is just take one and plug it up into the original equation here. If I change all the x's into 1, I would have 3 minus 1 inside the absolute value symbols. And the 3 minus 1 is 2, and the absolute value of 2 is just 2. So I have 2 times the 2 that's in here gives me 4, minus 1 gives me 3. Similarly, if x equals 5, I have 3 minus 5 is -2. The absolute value of -2 is +2. This 2 times that 2 is 4, minus 1 gives me 3 again. Point that I'm making here is it's not a bad idea to check your solutions here, especially if you're not super careful going through, not to check to see if you made a mistake kind of algebraically, but to see if you made a mistake going from this one equation to two equations. Anyways, that's how you solve absolute value equalities. The last thing I want to show you is how you solve absolute value inequalities. So we've seen a little bit about absolute value inequalities already. I guess that's not entirely true. We've seen some inequalities already. Remember that when you had a function, you had to look out for two things when you were figuring out the domain of a function. You want to make sure you didn't divide by 0 and you didn't take the square root of a negative number. So for example, if you had a function like h of x equals the square root of the absolute value of x plus 3 minus 5. You had something like this. And you're trying to find the domain of this thing. You'd be like, well, there's no squares going on here. I don't have to worry, or square roots. I don't have to worry about, there is a square root. There's no division going on here. I don't have to worry about dividing by 0. But there is this square root, so I have to make sure I don't take the square root of a negative number. So to figure out, to find the domain of h, what you would do is you would say that thing underneath the square root sign, aka the radicand, has to be greater than or equal to 0, so that I don't take the square root of a negative number. What you have right here is an absolute value inequality. This isn't the only place that absolute value inequalities can come up, but it's one thing that we've kind of seen already in terms of domain that might lead you to an absolute value inequality that might convince you of the need of this fourth thing down here, solving absolute value inequalities. There might be a case, and this isn't the only case, but this is one case, where you would want to solve this inequality. And you know how to solve equalities with absolute values in them, but what about inequalities? Let's do one. Maybe I can do it, maybe I'll do it with this graph right here. So what if you were trying to figure out when, and where should I go? I think I could squeeze this in here. When 2 times the absolute value of 3 minus x minus 1 is, I don't know, maybe less than 0. What if you're trying to solve this inequality right here? How would you do it? Turns out that it's harder than you may think. Easiest way would be graphically. 2 times the absolute value of 3 minus x minus 1 is exactly what I have graphed right here. So really what this is asking me is, when is the output for this function less than 0? Well, I graph the output of this function on the y-axis, so it's less than 0 kind of down in here. So it looks like it's from this point right here to this point right here. It appears, that's a dangerous word to use in math, that g of x is less than 0 on the interval from 2.5 all the way up to 3.5. And I want that interval to be open. I don't want to include those endpoints, because at those points exactly, at these blue dots, it's equal to 0. And I don't want to know when g of x equals 0. I don't want to know when this thing equals 0. I want to know when it's strictly less than 0. It appears from the graph that this would be my answer. I don't like looking at graphs and ballparking. Maybe you can get more clever and figure out why this in fact is exactly 2.5. But I also don't like relying on graphs. What if I didn't have this graph drawn? What if I didn't have a calculator handy? I like having multiple ways to do something. So yeah, you could do it graphically, but you can also solve this algebraically. The way you solve this algebraically is kind of clever. What you do is you say, damn, that looks hard. There's an inequality in here. However, if there were an equality in here, if this were equal 0, this would be easy. Okay, maybe not easy, but it would be the last problem that we did. Right? It'd be almost identical to this problem right here, except instead of a 3, I have a 0. So I could add 1 to both sides of the equation and say the absolute value of 3 minus x is equal to 1/2 after I divide both sides by 2. And so what that tells me is that this thing inside the absolute value symbol either equals 1/2 or it equals negative 1/2. Because if it equals 1/2, the absolute value of 1/2 is 1/2. If it equals negative 1/2, the absolute value of negative 1/2 is 1/2. I change this one equation into 2 different equations. The advantage to these equations is I can solve them. I could add x to both sides of the equation and subtract 1/2 from both sides of the equation and get 2.5 as x. I could add 1/2 to both sides of the equation and add x to both sides of the equation to get 3.5 equals x and get these 2 solutions. But these are not solutions to this thing. These are solutions to this thing, right? I changed the problem. You're like, yeah, good job. You solved it. Like, round of applause, but you didn't solve what I asked you to solve. You solved something different. So how happy could I possibly be? Well, the way you can solve absolute value inequalities is by solving equalities and then creating this thing called a sign line. And the way you create a sign line is you draw your number line. So here's 0 here. Here's, I don't know, negative 2 out here. This is not drawn to scale, but maybe 2.5 is here and 3.5 is here. And really the only important numbers that you have to put on your sign line are the solutions to the equality. So what I'm doing is I've already solved this guy, but I want to see how that gives me the answers to this guy. And the way you do it is by creating this sign line. And so what you do is you take your 2 solutions and you note that these 2 solutions divide your number line up into 3 different regions. Right? If you split things here and here, you now have 3 different regions. One region containing all of the numbers less than 2.5, one region containing all the numbers between 2.5 and 3.5, and a third region containing all the numbers greater than 3.5. And the nice thing to think about with inequalities is if this equality is true for some numbers and false for some other numbers, there's a number in between there where the stuff on the left equals exactly 0. So maybe the stuff on the left is less than 0 for a while and then it switches to being more than 0. A nice property of numbers, really what we're playing on here is the fact that this function is continuous, but that's getting into some kind of higher level topics. A nice fact that will be true is the only way this statement switches from this thing on the left switches from being less than 0 to greater than 0 is at the points where it equals 0. So that's why I solved where it equals 0. These are the only spots where I can switch from having true statements to false statements. So if I test any number in region 1 and I find that this original equation is false, so maybe I test 0 because 0 is a number in region 1 here. If I find this equation is false, not only is it false at 0, it's false for all numbers in this region. Everywhere from negative infinity up to 2.5. So that'll be really powerful. I won't have to test all the infinitely many numbers there are out there. I'll just have to test 3 numbers, one from each of these regions. And the way I'll test them, I'll test region 1 first. Pick any number you want from region 1. I like picking 0 because 0 often makes math work out nicely. But you can pick any number. You can pick -2, you can pick -1, you could pick +1, +2. You could pick 17 divided by 312. I don't know why the hell you do that. It'd make things really difficult, but because that fraction is in this region, you could pick it. And once you test whatever number you pick, that'll give you so much information, not just about one number. So the way you test it is you plug it into the original equation. You ask yourself the question, is it true that 2 times the absolute value of 3 minus 0, note I changed the x into a 0, minus 1 is less than 0? And I'm going to put a question mark here because I don't like writing a statement that may not be true without a question mark. In fact, this statement's going to be false because 3 minus 0 is 3, and the absolute value of 3 is 3, and 2 times 3 is 6, and 6 minus 1 is 5. And 5 is not less than 0. In fact, 5 is greater than 0. So what I'm saying is that 0 is not in my solution set. And if 0 is not in my solution set, no numbers in region 1 are in my solution set. I'll represent that with a big X here. Let's test region 2. Pick any number you want between 2.5 and 3.5. I don't know, 2.7, 3.4, pi, any number you want. Because I like keeping things simple, I'm going to pick the number 3, the only whole number in this region, and test that. Is it true that 2 times the absolute value of 3 minus 3 minus 1 is less than 0? Right? Wrote this thing again, except I changed all the x's into 3's. Well, 3 minus 3 is 0. Absolute value of 0 is 0. 2 times 0 is 0. So the left-hand side is just equal to -1. And in fact, -1 is less than 0. So yes, that's fantastic. Not only is 3 in my solution set, but the entire region 2 is in my solution set. I'll put a little check mark here. Kind of low on room, so I'll jump over here to test region 3. Pick any number you want that's greater than 3.5. 4 maybe, 10 maybe, whatever the hell you want. It doesn't matter as long as it's greater than 3.5. I want to figure out is 2 times the absolute value of 3 minus 10 minus 1 less than 0? Question mark. It's not, because 3 minus 10 is -7, and the absolute value of -7 is +7, and 2 times 7 is 14, and 14 minus 1 is 13, and 13 is greater than 0, not less than 0. So these are not solutions, meaning these are not solutions. So what that tells me is that all of the solutions to this thing are region 2. In other words, all the numbers between 2.5 and 3.5. I do not want to include 2.5 and 3.5 because at 2.5 and 3.5, those came from solving when this equals 0. And the question asked me when it's less than 0. If it asked less than or equal to 0, I would want to include those points, but it just says less than 0, so I do not want to include those points. What I'm getting at is from these tests, I can get that my solution set, I don't know where the hell I can write this, so my answer is region 2. Well, region 2 is all of the numbers in between 2.5 and 3.5. So I get in interval notation all the numbers from 2. Wait a minute, that's exactly what I wrote right here. Algebraically, I confirmed what appeared to be the case based on the graph. That is how you solve absolute value inequalities. So to summarize it, when you're solving an absolute value inequality, first change it into an equality. Because in your mind, you're like, wait, that was checkpoint 3. If you're doing a problem from section 4 here, make it a problem from section 3, because presumably by the time you got to 4, you know how to do 3. Solve 3, but then recognize that these aren't your answers right here. Test those answers using this idea of a sign line. This idea of a sign line is worth learning. There are other ways you can solve this, but you have to be really careful keeping straight the inequality that you have and what regions you're in. It's very difficult to solve these inequality without a sign line. There's other ways you can do it, but I don't recommend it for several reasons. One, because you'd probably screw it up. No offense to you, I don't know your mathematical ability, but most people, I could probably create a problem that's complicated enough where you'd mess things up if you did not use a sign line like this. Also, there will be other problems, other inequalities, other strange problems, not with absolute values in there, but with other things in it, that solving them, a sign line will be super useful. So get some practice with this method, because it won't be a method that's only useful in this section. It's a method that'll be useful in lots of other sections as well. I think that's all I got to say about these 4 topics. So that's all I got to say about section 1.6.